Hello, we are Group 4, and we will be focusing on understanding the different aspects of vehicle behavior and the external factors that are more likely to cause traffic accidents. So, NYC DOT is starting to implement new connected vehicle technology in NYC as a way of making it safer for us to drive and cross the street, especially during heavy traffic. This new technology is part of DOT's Vision Zero initiative, in which the DOT is aiming to eliminate and reduce traffic related deaths and injuries, as well as reducing damage to vehicles and infrastructure. A major problem in NYC is traffic related accidents that leave many injured or even killed. The NYPD reported that in just March 2022 alone, there were at least 8,600 motor vehicle accidents, and over 35% of these accidents include injury to cyclists and pedestrians across all boroughs, as well as fatalities. This CV technology that we are focusing on is V2V communication to alert drivers so as to aid them in avoiding crashes or reducing the severity of injury. The technology uses aftermarket safety devices, or ASD, that have been fitted to over 3,000 vehicles that are driving throughout specific areas of Manhattan and Brooklyn. These devices use GPS location information to identify a vehicle's current location, its path history, and the location it is heading towards, and this information is then processed and shared with nearby vehicles and forms alerts regarding potential hazardous situations. So the dataset that we are focusing on is the BSM dataset, which is the Basic Safety Message Dataset, because this dataset includes information on vehicle behavior that was collected immediately before and immediately after a vehicle received a safety warning. In our project, we are focused on learning what are the more common warnings given to vehicles and what factors cause the most warnings to occur. This allows us to learn about the most common causes for vehicle accidents and then research steps to reduce the likelihood of accidents and prevent crash-related injuries. So we are using this BSM dataset because we want to study certain characteristics of vehicle behavior, such as the time of day that a vehicle received the warning, what day of the week was it, the direction it was moving, what type of warning it was given, what was the vehicle's speed, what was its acceleration, and what borough was the vehicle moving in when it received these warnings. In the next few slides, we'll be discussing a number of hypotheses in order to determine the correlation between certain aspects of a vehicle behavior and what caused it to receive a safety warning.
For the hypothesis one, we wanted to talk about the relationship between the time period and the traffic accidents. So we have two questions. The first one is, are traffic accidents more likely to occur at night than in the morning and afternoon? Because we know that in the evening it may be more dangerous. So we calculate and count the number of the events separately in the morning, afternoon, and evening. And we found that, oh, that's not true. In the morning, more events may be occur. So the answer is no. And the second question is that, are traffic accidents more likely to occur on weekends than on weekdays than on weekends? Because everyone needs to go to work or study, so they need to drive the car in the weekdays. And we found that the answer is yes, and more accidents will be occurred in the weekdays. And we collect all the information for the events of each time period in a week. And we can see that the trend that the traffic events are more likely to occur on weekdays instead of the weekends, and occur on morning and afternoon instead of the evenings. So the possible reason is that the people are likely to use their vehicle on weekdays, so that the cases may be higher. So we can see this figure. And also the method we use is the k-means. It's a clustering method and to help us to know which data have the similar features, so we can classify this data and then to know something. So on the right hand, we can see if we choose the cluster number 2 and 3, and we can see the different results. So interesting is that in the evening classification, when the cluster number is 2, we can see it's separately divided into two parts. The first 4 day and the last 3 days. So we can know that in the Friday is like the weekend, because everyone have no job tomorrow. So the situation may be different with the weekdays. So the conclusion is that for the events number in the morning, weekdays are separated to the weekend, and for the events number in the afternoon, weekdays are separated to the weekend. But for the events number in the evening, the Monday to Thursday are separated to the last 3 days in a week. That's all for the first part, the hypothesis 1.
This is the hypothesis 2. So what is the vehicle amount and speed distribution in 3 districts during the daytime? So as we can see, I use the data set for the 3 districts and the different time range and the car amount. So we can see for the total vehicle amount during the daytime, at the left graph, we can see the Manhattan has the highest, so it means Manhattan has the most vehicle amount. And for the bottom one, the time of day connected vehicle distribution in New York City, we can see the arrow of the green part has the highest percent. It means the vehicle volume is very, very high during the 10 a.m. to 3 p.m. And the following one is the AM area, the pink one, which means 6 a.m. to 10 a.m. And these are the total things. If we divide this into 3 districts, we can see in Bronx and in Queens and in Manhattan, there's always MD time area occupy the highest percent of the vehicle amount. And especially in Queens, we can see the MD time and AM time contain the most 90% of the vehicle amount in this area. So if you want to drive during the daytime, if you want to avoid the high vehicle volume, you may avoid the time during 10 a.m. to 3 p.m. and 6 a.m. to 10 a.m., especially in Queens district. And also, what about the speed distribution in 3 districts during the daytime? You can see if we can solve the speed distribution, the government can formulate corresponding rules to regulate and control, and then decrease traffic accidents risk. I also divided this data as 3 districts: the Manhattan, Bronx, and Queens. We can see the cars are always within the speed of 20 to 40 mph, and Manhattan always get the highest vehicle amount. For the hypothesis 3, what is the even type distribution in 3 districts? As we can see, the right side, the even type explanation. For instance, the FCW means forward crash warning. If we can figure this out, we can let the ASD is able to inform drivers to prevent event warning and then decrease traffic accident risk. And for the total event type, we can see the SPD comp has the highest warning percent. So what does it mean? It's curb speed compliance. So we need so the ASD can inform drivers to pay more attention for this kind of warning, the curb speed compliance. And in Manhattan, Bronx, and Queens, we can see they have different high percent of the event type of the warning event type. For instance, in Manhattan, it's the same as the total event type, the SPD curb speed compliance. So the drivers may pay more attention when they drive in the area of Manhattan. And for the Bronx, the FCW occupies the highest percent in this line graph. So what is FCW? Forward crash warning. So drivers may pay much more attention when they drive in the area of Bronx for the warning, the forward crash warning. And also the Queens, the forward crash warning also occupies the highest. So the driver needs to pay more attention.
According to the problem statement, our team uses BSM, Basic Safety Messages datasets, to address this problem. Choose 5 of these parameters to describe the state of the vehicle, which are yaw rotation, longitude acceleration, vertical acceleration, and orientation. First, verify the correlation between the parameters for reducing the interaction between parameters. Because parameter 2 and parameter 5 have a strong correlation, our team just use parameter 2 as the description of longitude acceleration of the vehicles. The rotation rate of the vehicle about its vertical axis in 0.01 degrees per second. Positive yaw is to the right clockwise. According to the definition of yaw acceleration, it concluded that the vehicle is generally yawing in a counterclockwise direction in a dangerous state. For the lateral axis, a value of 2000 is used for values greater than 2000, and the value of negative 2000 is used for values less than negative 2000. Positive values means right side. It is concluded that the vehicle generally has a horizontal acceleration to the right in a dangerous state. For the longitude and vertical axis, the acceleration is normally distributed. The average lateral acceleration is 0, and the average longitude acceleration is 50. Therefore, it's concluded that the vehicle usually generates an acceleration of 1g to the back when warning occurs.
In the conclusion part, for the hypothesis 1, traffic events are more likely to occur on weekdays than weekends, and traffic accidents have little relevance with time period of 1 day, specifically for the days and nights. In hypothesis 2, Manhattan always has several times more than Bronx and Queens in vehicle amount. The peak vehicle volume time is from 6 a.m. to 3 p.m. People in New York could avoid this peak time to go out or try to take the public transportation such as subway and bus to go out. In hypothesis 3, the most common event warning is curb speed compliance. Different areas reflect the different high-risk warnings. Drivers should pay more attention if the warnings always happen in specific areas. Researchers will focus on adjusting ASD, which can inform drivers to prevent event warning and then decrease the traffic accidents risks. And for the hypothesis 4 and 5, vehicles are generally yawing in a counterclockwise direction in a dangerous state and have a horizontal acceleration to the right in a dangerous state. Vehicle usually generates an acceleration of 1g to the back when warning occurs. So that's all. Thank you.